Now, before we tackle continuous probability distributions, let's just remember again what continuous data really is and how the probabilities associated with it might look. So if I was to take an example with discrete data, let's say I've got 5 lollies and I want to put the lollies into 2 bags, and I'm looking at the probability of the bags containing different numbers of lollies, I'm going to get nice whole numbers like 0, 1, 2, 3, 4 or 5 lollies in each bag. Whereas if I take 5 litres of water and I tip it into 2 buckets and I look at the probability that either bucket ended up with a certain amount of water, well, that amount really comes down to how I measured it, and the number of decimal places that I used, how reliable my equipment was, and in fact the probability of any one particular volume occurring in either bucket is going to be 0. Now it seems a bit strange, doesn't it, to say that we can't estimate the probability of either of those buckets having a particular quantity of water in them. And that's because there are an infinite number of quantities, so finding any one is virtually impossible. But what we can do is we can look at the probability of a range of values occurring. And then we can use reasonable logic to come up with some really simple probabilities here. So if I know that one bucket or the other has to have anything from 0 up to a total of 5 litres in it, assuming that when I tip the water randomly into the buckets, it all goes into one bucket or the other, I could reason on the probability that one of the buckets has, say, 1 litre or less. Because I can say, well, having between 0 and 1 litres, that's 1 litre out of a total of 5, the chances of that must be 1/5. And again, here I'm just using number of favourable outcomes out of total number of outcomes. What's the probability that one of the buckets has between 2 and 4 litres? Well, I can say that's 2 litres right up to 3.99999 litres. That's a 2 litre amount I'm interested in. Out of 5, the chances would be 2/5. Now remember that the cumulative probability distribution function adds the probabilities together. So when we looked at it with discrete data, we had columns of increasing size and our polygon was always going up, wasn't it? Well, the same strategy sort of applies here, except that we can't graph the columns because there's infinitely many of them. But what we can do is we can look at what the polygon would look like, and often it makes kind of a smooth curve, or in other words, a function, and that's where the f part comes in here. Now, if what we're measuring has a nice reliability about it, then we can build that function quite easily. If we're measuring, say, area, we can use area formula. If we're looking at measuring volume, we can use the formulas for various volumes. If we're measuring time, then we can look at proportions of time. So now an example. A chook wanders in a circular pen with a radius of 6 metres. Let x, and notice this is big X because this is the random variable, let x be its distance from the centre at any time, and the function of x, now you'll notice the notation here, big F is what we use for a cumulative distribution function. So this is going to be a CDF in its own right. And we're letting f of x, where this is f of little x, where little x is all of the outcomes that you could possibly get. In other words, all the distances that the chook could possibly be from the centre, is equal to the probability that big X is less than or equal to little x. Now remember what our CDFs look like. They're always increasing. Let's write that down. Always increasing. And they give us the probability that x is less than or equal to something. So here we want to say what's the probability that our chook is less than or equal to a certain distance from the centre. So the first thing that I would do here, before even reading the rest of the question, is to draw a picture and say, here I've got my circular enclosure, it's got a radius of 6 metres, and if what I'm interested in is the probability of the chook being a certain distance from the centre, let's make that defined area of a certain distance from the centre, and because we know that it will have a set radius, we can call that radius little x. Now clearly little x could be anything from 0 to 6, so as I define my function of x, I'm going to just put that in as a little reminder that x has to be between 0 and 6 for this to make any sense at all. And now I can go ahead and have a look at what I'm actually being asked in this question. Find the probability that the chook is less than 2 metres from the centre, so in other words we'll need to let little x be 2, and find the probability that the chook is somewhere between 2 metres and 5 metres from the centre. So I'll have to do a little bit more thinking for that one. So let's just start by defining what our cumulative distribution function is going to look like. Well, it's the probability that our chook is less than or equal to a certain distance from the centre. So if we say, well, if it's x metres from the centre, the chance of that happening is basically the size of this inner area compared to, or as a fraction of, the size of the whole pen, because that'll give me the fraction, what I want, out of the total of what there is. So I've got the area of the inner circle over the area of the entire enclosure. Does that make sense? Remember, with our probabilities, we always put the favourable outcomes over the total outcomes, and that's exactly what we have here. So now I can come up with a little formula for this quite easily. I know the area of a circle is pi r squared. So here I need pi, not r, but x squared over pi times 6 squared, which is 36. So I'll write this as 36 pi. Now clearly the pi's are going to cancel out, so what I then end up with is just 1/36 x squared, or I could write that as x squared on 36. Now if I wanted to graph this, I could. It's a function, so obviously we should be able to graph it. We'll only be able to graph it on this domain, but I can do a simple graph now. Now if I graph not y but big F of x, let's put that on the vertical axis. Let's put little x on the x-axis. And now this looks like a parabola, doesn't it? So it's a parabola, but it's a sort of short, fat one, not a steep one. And that 1/36 tells me that it's basically really stretched out like this. But it's going to have that basic parabola shape. Now it only really exists from values of x, 0 up to 6. And I can reason what this will be. When I plug 6 in here, 6 squared is 36. 36 divided by 36 is 1. And in fact, this is what I should make sure that I get every time, because a little thing that we can write down, this should probably be somewhere important, the function of 0 should be 0, because in a cumulative distribution function, the probabilities need to accumulate, don't they, until we end up with a certainty right up the top. So the probability of our upper value here needs to be 1, because it's a certainty that x has to be between 0 and 6. Okay, so I've developed my function of x. What I need to do now is answer the questions I have been asked. What's the probability that the chook is less than 2 metres from the centre? Well, here we're letting little x be 2. So we're saying it's going to be the function of 2, which is 2 squared is 4, 4/36, which is, of course, 1/9. Now to answer B, what are the chances that my chook is between 2 and 5 metres from the centre? I'm going to change my picture slightly so that you can picture what we're doing. If I have this inner area as being a 2 metre radius, and this slightly bigger one as a 5 metre radius, then what I'm effectively asking is, what is the chance that my chook is sitting in this donut-shaped space? Now, remember what this means. This means, what is the probability that my chook is less than or equal to anything I want to know? Well, I want to know the probability of my chook being inside this 5 metre circle, and then if I subtract the probability of it being in the 2 metre circle, I'll have what's left over, which is the donut-shaped section. So I effectively want to find the probability that it's in a 5 metre circle, and I can do that by just finding f of 5. And then I want to subtract f of 2. Now I've already found f of 2 up here, so f of 5 is going to be 5 squared, or 25/36, minus 4/36, and that's going to give me 21/36, which I can simplify down, dividing top and bottom by 3 to get 7/12.